load correctly here. Here we go. All right. So yesterday we left with this molecule. And what I was asking you guys was to predict which proton is going to be more acidic, the blue proton, or the one circled in blue, I guess, or the one circled in red. And we kind of had to rush out because we were running out of time. So I want to step back and address this in more detail. And what we're going to do is identify the most acidic proton in a variety of different molecules. But I'll show you guys a couple hints first. The first hint is when in doubt, draw both possible, or both or all, possible conjugate bases. Oop. And compare their stabilities. All right, so if we go to this example, let's draw the conjugate base for this one. So I'll do minus H plus, so we'll remove that blue proton. If we do that, we've now got carbon, carbon, carbon. We've got a negative charge here, and we've got two R groups. All right, so that's one possible option. The other possible option is let's remove this red proton. And we've got carbon, carbon. Let's finish drawing this all in. What we have to do is we have to ask ourselves, which conjugate base is more stable, the one on the left or the one on the right? This gets tricky. So let's go back to our order of priorities that we went over yesterday. And yesterday I created this long list of things to watch out for. Number one was electronegativity. So if we look at the conjugate base, one of them has a negative charge on a carbon, the other one has a negative charge on a carbon. So we're at a tie. All right, we go down the list. Atomic radius, what's bigger, carbon or carbon? We're tied. So we go down the list. We check for resonance. Okay, let's go back and see if there's resonance structures for either of these. All right, the one on the left. Can I move this negative charge down here? No, not without creating a Texas carbon. That's not allowed. What about moving it over here? No, not without creating a Texas carbon. So no resonance. But this one, we can actually take this negative charge, move it down here, and move the negative charge over there. So if we compare the conjugate base for removing that proton, we have a new resonance structure. And this one has resonance. And a lot of people will stop and say, well, hey, Jeff, you mentioned hybridization yesterday. The one on the left is more stable due to hybridization. Shouldn't that be more stable? Exactly, it's a lower priority. So you want to work your way down that list. So remember that resonance trumps hybridization. All right, so now what I'm going to do is I'm going to give you guys a couple of molecules, and I want you to identify the most acidic proton on these molecules. All right, first one. I'll label this one as red out here, and I'll label these ones as blue. I want you to determine whether or not the red proton is more acidic or the blue one. And then once you think you've got that, you can talk with the neighbor. And then I'm going to give you guys a couple more challenging ones, so let me draw these out. First one's pretty straightforward, hopefully. Oop. There we go. And we've got a lone pair over here. And then I've got another one here. You guys are going to get really good at drawing hexagons this quarter. You wait. All right, we've got one over here. And then one here. Oh, I keep on writing B. All right, there we go. So here's 3 different molecules. I want you to determine which proton's more acidic, the red one or the blue one, and try to use that list of priorities to distinguish which one's more acidic. And if you get stuck, draw out both conjugate bases. You guys are welcome to talk to each other. Do I have any volunteers for the first one to explain red versus blue? What do you think?
The red, because O is more electronegative than carbon.
Yeah, exactly. So if we're comparing removing the red proton, the blue proton, if we remove that red proton, the negative charge is on the more electronegative oxygen atom. So in this case, electronegativity wins. And we can circle this and we can say most acidic conjugate base will have a negative charge on the more electronegative atom. Perfect.
I have a question.
Yep.
So if you go through the list, you have to go through the whole list, or you just stop at the first one?
Try to stop at the first one. And one thing I will say is this list isn't the absolute priority. Sometimes there are weird exceptions, but it's a good guide.
Okay.
Yeah. All right, does anybody have a solid guess for the second one? What do you think?
Blue.
Blue. Why do you think blue?
I guess.
You guessed. Does anybody have an educated guess with a hypothesis behind it? I'm not saying you're wrong, but
I'm going with red because you can create a resonance structure with shifting the electrons that are then created on that carbon up to the down to the pi bond and then move the pi bond over to the nitrogen.
so if we remove the red one, it actually can't delocalize because that p orbital is already taken up by that pi bond, right?
Yeah.
But what about the blue one?
You can. It can't. How can move down?
Yeah, so just for the sake of argument, let's draw this. So let's say I remove this blue one and we've got a negative charge there now. I could go ahead and I could say, all right, let's move that negative charge here and that charge over there. So that one does have resonance. You are on the right track. It is absolutely resonance related. But if we remove the red one, that p orbital is already occupied by a pi bond. So if we go through, let's label this. We'll say most acidic conjugate base can delocalize via resonance. All right, did anybody have a educated guess for the last one?
Red.
What do you think? Red? Okay, so why did you think red?
Nitrogen's more electronegative than carbon.
Yeah, exactly. So if we do the red one, the electronegativity trumps the resonance in this case. So it's a lot easier to remove a proton off of a nitrogen than it is off of a carbon. So in this case, again, we go down that list and we can say that this is most acidic due to electronegativity. I'll just write EN instead of writing it all out again. All right, you guys ready for a challenging one?
No.
You guys are so enthusiastic about this. All right, I'm not even going to draw the hydrogens in, but remember that the hydrogens are assumed. So we're using bond line formula. Where is the most acidic proton on here? All right, if you think you've got it, explain it to your neighbor. Does anybody have an educated guess that they've talked out with the neighbor? All right, I'll give you guys another minute. I'll still give people a minute. Seems like people are working on it. I'll make it a little easier and draw out some of these protons.
Well, no, let's just go around. Take it off.
All right, raise your hand if you think you got it. All right, we've got a few people. What do you think?
Right in the middle, because it's got two oxygens right there that can help support the negative charge.
All right, so let's try pulling off this red proton. So I'm going to go minus H plus up here. And I'm going to switch back to our bond line formula. So we've got a negative charge. Oh, shoot. Negative charge here. This is pretty neat. So this negative charge can delocalize up onto this oxygen. So we get a double bond here and a negative charge on this oxygen. Or this negative charge can delocalize all the way over to this other oxygen. Oops. Let me fix this. This one's the double bond now. This is the double bond. So if we remove the blue one, it does have a resonance structure where it can delocalize. But if we remove the red one, it actually has two different resonance structures it can delocalize on. So this is a really unique example. And so if we were to draw the hybrid structure of this conjugate base, we would actually have a partial negative here, a partial negative here, and a partial negative there. So that makes it a very, very stable conjugate base. So like I said, if you're ever stuck, draw out both conjugate bases that are possible or all of them that are possible, and then try to rationalize going down that list from 1 through 4 like we've been doing. Does that make sense? Resonance pops up a lot in this class, so make sure that you understand resonance from chapter 2 because it's going to be carried through this chapter and even into following chapters. All right, so now that we've identified the most acidic protons and molecules, we have to also identify the most appropriate base. So did you guys grab that common bases handout that I had the other day?
Yes.
All right. So pull that out if you have it in your notebook, and we're going to go over what that means today. All right, so let's say we've got our generic acid-base reaction with HA plus our base. We spent a lot of time talking about this conjugate base. And remember that for the deprotonation of HA to be favored, the pKa must be lower than the conjugate acid. Oops, sorry. And HB plus is our conjugate acid. All right, so let's take an example of what I mean by this. An example I have is using acetylene. And acetylene's got H, carbon, triple bond, carbon with the hydrogen. The question is, what base can we use in order to deprotonate this? So what do you think the first thing we need to do is if we're going to determine the best base? Yeah, find out the pKa of your acid. So, okay, let's check our pKa's, and if we go through that chart that I gave you, you'd find the pKa of the acid is going to be 24, which means that pKa for HB must be greater than 24. Perfect. All right, so what we do is we can go through our acids and bases handout, but first let's take a look at some examples and try a few different bases. So let's do one example, and let's say I've got our acetylene, and the base I want to use this time is hydroxide. So something like sodium hydroxide. We'll have this in equilibrium. We'll try to form acetylide. And what will our conjugate acid be if we're using hydroxide? H2O. What's the pKa of H2O?
15.7.
Yeah, it's 15.7. Which means, conversely, that this is not a good base. Okay, let's try using a different base then. So instead of using hydroxide, let's use NH2 minus. This is called amide. And this is in equilibrium. So again, we're going to try to deprotonate our acetylide, or our acetylene, and form an acetylide ion. And then what would our conjugate acid be? Yeah, NH3, ammonia. What was the pKa from our problem of the day for ammonia? 38. So is amide an okay base for deprotonating acetylide? Yeah, so in this case, this one is a good base. So if you go through, I've got a big list of common bases in organic chemistry. I wouldn't say this is an exhaustive list, but I tried to order it from weakest to our strongest bases. So if you look, sodium bicarbonate, it's also known as baking soda. It's a pretty weak base. We use it in cooking. The conjugate acid for it has a pKa of 3.6. So that's relatively acidic, which means sodium bicarbonate is not a great base. Pyridine is a little bit better. The conjugate acid has a pKa of 5.21. Then we can go to potassium carbonate, has a pKa for its conjugate acid of 10.3. Triethylamine, its conjugate acid goes to 10.75. Sodium hydroxide, we said water has a pKa of 15.7. And then we can start going into some other bases, like potassium butoxide. The conjugate acid has a pKa of 17. So on the left-hand side, I call these weak bases in quotes. Remember, acidity and basicity is all relative, right? So in the grand scheme of things, these are relatively weak. If we switch over to the right-hand side, we've got super-duper strong bases. We've got sodium hydride, sodium amide, lithium diisopropylamine, which is commonly referred to as LDA, and then we've got N-butyl lithium. You can see the pKa's for these conjugate acids are all above 30, so these are excellent, excellent bases. Question a lot of people ask me is, well, why don't we always just use the strongest base available? What do you guys think?
Strong base and a strong acid.
Too reactive.
Yeah, so we said during our problem of the day that a really, really strong base is something that's really, really unstable. So if you've got a really, really unstable base, there's a chance that it will react with moisture from the air. So these last two, if you squirt them out of a syringe, will actually catch fire from the humidity in the room. So sometimes people avoid using them for that reason. Another reason, too, is if these are super duper reactive, they could even react with your reaction solvent. So we do have to choose the appropriate base, but we don't want to overshoot our base. And we're going to talk about choosing the appropriate solvent, too. So let's take a practice swing at this, and I want you guys to choose a base for me. I want you to pick a base to deprotonate the last molecule that we were looking at with our acidity trends. And I'll give you guys a hint with its pKa. The pKa for this is going to be about 9. And we know which proton's coming off because we just assessed that. So see if you can find something on your chart that will work for that. I'll give you guys a minute. Raise your hand if you think you've got an appropriate base. All right, it looks like most people are getting there. So does anybody want to volunteer a base that they chose? What do you think, Alan? Potassium carbonate. So if we look at potassium carbonate, it's got a pKa of 10.3 for its conjugate acid. So we can actually deprotonate this using potassium carbonate. We couldn't, on the other hand, use pyridine, and we couldn't use sodium bicarbonate because those conjugate acids are more acidic than our original acid, right? Yep.
Well, wouldn't, like, practically, if you can use water, would you want to? It's cheap. I mean,
So if we use water, we get H3O plus as our conjugate acid, and that would actually be stronger than our original acid. Yeah, that is a good point, though. If we can, we normally try to use the most environmentally friendly / cheapest option available. We don't want to go overboard and do something that's dangerous or expensive. Did you have a question?
Yeah, so the base we choose, the conjugate acid for it has to be less acidic than our original acid?
Yes, exactly. So let's even put that down. The conjugate acid for the base must be greater than 9. All right, let's say I get a little overzealous and I say, you know what, I'm going to throw an N-butyl lithium at this. What do you think might happen? Not necessarily. And let's talk about it. If we use N-butyl lithium, though, we have to be super duper careful with our reaction conditions, right? So I said that N-butyl lithium and lithium diisopropylamine will react with humidity or water violently, which means we don't want to use water as a solvent, but we may have to choose an appropriate solvent for this reaction. And that's where the other side of that handout comes in handy. So one half talks about bases, the other half talks about selecting an appropriate solvent. So let's take a look at this. And let's talk for a minute or two about solvents. What is a solvent and why do we use it? Does anybody have a hypothesis or explanation?
Associate molecules.
So maybe helps dissociate molecules.
You can say a media that doesn't react, that helps them mix.
Yeah, exactly. It's a reaction medium. So and I abbreviate reaction RxN. So solvents are a reaction medium. They sometimes will facilitate a reaction occurring, but they should more or less be inert, meaning we're not ideally making or breaking bonds with our solvent. Meaning they're non-reactive. So let's take an example. And in this example, we're going to use our previous molecule. And I'm going to do a little bit of overkill. I'm going to use sodium amide, which is NaNH2-. And I'm going to run this reaction in water. Okay, so this is our solvent. This is our base. And this is our acid. What do you think will likely happen? Let's stop and think about this. What was the pKa of our acid again? 9. What was the pKa of our solvent? 15.7. Okay. Actually, let me change this a little bit. I'm going to use a better example. I apologize. Let's backtrack. I'm going to use this one. We're going to use one half of it. This will be a better example, trust me. This one has a pKa of 19.2. Water has a pKa of 15.7. So if we have a base, and it has the option of plucking the protons off of our acid or the protons off of our solvent, which one's it going to go after? Yeah, it's going to go after our solvent. Our solvent in this case is actually more acidic than our acid of interest. So in this case, we would end up with unreacted starting material plus NH3 plus sodium hydroxide. So in this case, one thing we have to watch out for is with our solvent is you don't want your solvent to have a lower pKa than your acid of interest.
What if that happens?
Yeah, that's a good question. So in this case where our solvent has a lower pKa, our base will just preferentially deprotonate all of our solvent, and we don't deprotonate the acid that we wanted to deprotonate, right? So we do have to choose a solvent usually with a higher pKa than our acid. Otherwise, we'll just react all of our base with our solvent and end up with nothing but sodium hydroxide out in the end. Yep.
I'm sorry, I missed where you reasoned that it goes to a smaller pKa.
So if we're comparing our acid and our solvent, which one's more acidic?
Oh,
Yeah, our solvent in this case is more acidic, so our base is going to react with our solvent before it ever has a chance to react with the acid on the left-hand side. Yep.
In that case, wouldn't the acid be the solvent? And not almost because there's like you could like fill the whole thing full of that acid, right? And if you follow the rules, it wouldn't even react. So technically, it would be solvent, right?
Yeah, the point is you want to choose a solvent that won't participate in an acid-base exchange.
Okay.
So ideally, your solvent should have a higher pKa than anything else in that beaker. I will show you guys kind of a weird exception to that. Let me slide this down too. Was there a question back here?
Yeah, so if the base only react with the solvent, why is the need to add acid?
So in this hypothetical situation, I'm saying we're trying to deprotonate this acid on the left-hand side.
Okay.
And the base I chose was sodium amide, and I chose the solvent water. In this case, if I chose the solvent water, my base would immediately deprotonate my solvent and wouldn't ever have a chance to deprotonate what I wanted it to. And so that wouldn't be a good solvent to choose for this reaction.
So it doesn't matter if we have acid or not in this solution. I mean, because it doesn't react to the acid, we don't have.
Yeah, this was just a hypothetical situation. And I'm saying I did want to deprotonate my acid, but in this example, this reaction will not proceed forward. It will not deprotonate our acid. Instead, it will deprotonate our solvent.
Okay.
Let's take a look at another example too really quick, and then I'll come back and answer your question. All right, so now the question is, that was a crummy solvent to choose. We need to choose a better solvent. So again, I'm going to choose the same acid, and I'm going to use sodium amide. And this time I'm going to use ammonia. All right, now if we look at the pKa's for this, we've got a pKa of 19.2. And then we've got a pKa of 38 over here. Do you guys think we're in good shape now? Yeah, so let's draw out the products that we would get from this. we would end up with our deprotonated acid, which also has resonance delocalization, so we could draw that. What other product would we end up with? So our amide that we used would grab that proton and become NH3, and then we'd also have solvent around that's NH3. All right, so the conjugate cation or countercation would be sodium here. So oftentimes what chemists do as a kind of clever trick is they choose a solvent that is the same as the conjugate acid that's formed, right? That way you don't have to deal with separating out more than you necessarily want to. You only end up with a clean mixture in this case. So this is a really common trick. All right, so if you are looking for good solvents, I included a list on that backside. So let's take a look at that list. And I've got them separated into categories, and we're going to talk a lot about these categories when we get into some of our reactions. But the first category is referred to as polar protic. Protic means that you've got a proton coming off of an oxygen or nitrogen typically. So in this case, we've got ethanol. It's a pretty common solvent that we use. That's got a pK of 16. Methanol is about 15.5. Water is at 15.7. These are really common solvents to use. They facilitate some reactions, meaning they make them happen at a faster rate. And they're environmentally very friendly, right? Ethanol is pretty green. We could dump it on the floor and not panic if we breathed in some of the vapors. If we go down the list, we've got polar aprotic, meaning we don't have a proton coming off of oxygen or nitrogen. So do you guys see how polar protic doesn't have any of those protons coming off electronegative atoms? These are also commonly used. So acetone's one, acetonitrile another. Dimethyl sulfoxide, that DMSO is another one. Dimethyl formamide is another. Tetrahydrofuran, also referred to as THF, is common. And then we've got our non-polar solvents like diethyl ether, benzene, toluene, dichloromethane, chloroform, and carbon tetrachloride. And a lot of people will ask me, well, why don't we always just choose something like carbon tetrachloride? It's got a pK that's not even applicable because it doesn't have any protons on it. Does anybody have an idea? First of all, carbon tetrachloride will cause cancer. That's a good reason. Second reason is oftentimes reactions have to be run in a solution that contains either a polar protic solvent or a polar aprotic solvent. So once we get into reaction classification, we have to choose an appropriate solvent, and I wanted to give you guys kind of a broad overview of all of the different solvent classes.
So is the ammonia that we just used in that previous reaction not a common solvent?
Ammonia is not a common one that you see used in a lab. We will see it in our book, but ammonia is actually a gas, and working with gases is not super common. People do it if they have to, but most of the time we try to avoid it and choose a more gentle base.
Okay, so this last reaction is not a common.
Yeah, I mean, if we were in a lab, we would probably try to find a better base than sodium amide.
Okay.
Yep. Are there any other questions? Yeah. All right. One thing is hang on to your problem of the day, bring it in tomorrow. We're going to do an in-class activity tomorrow. If you're in Thursday or Friday lab this week, we do not have lab. Your lab reports will be due the following period, and I won't have office hours this Friday. I'm going to be out of town. Yep, problem of the day is due Monday.